Welcome, everybody. My name is Adam Frey, and I'm the Global Category Manager for Software here at 3D Systems, and I would like to thank you for joining today's 3D Scan to 2D Pattern webinar. This webinar is being jointly presented by 3D Systems and ExactFlat. I appreciate you joining us today, and I hope you'll be able to join us on future webinars as well. A few housekeeping items before we get started. As you may have noticed, all attendees' lines were muted upon joining the webinar. Therefore, please use the Q&A button on your screen to submit any questions as we go along, and we will take some time to answer questions at the end of today's webinar. Additionally, we will make the answers to all frequently asked questions available for all of you who have attended. Also, in a couple of days, you'll be receiving a follow-up email with a link to view the recording of this webinar, as well as information regarding how you can trial the software being demonstrated today and a special offer from 3D Systems and ExactFlat. Once again, thank you for joining us today, and now let's move on to today's presentation. Manufacturers in a variety of soft goods and technical textile industry segments, some of which are shown here, are facing increased time to market and profitability expectations. And recent data has shown that the benefits of transitioning to a 3D digital process are undeniable for addressing these challenges. Still, the biggest hurdle to accessing these advantages has been a reluctance for companies to take on the challenge of adopting 3D design. As you will see today, 3D scanning eliminates this challenge. What we'll show in this presentation is an overview of the entire process from 3D design, capture and cleanup, flattening, and then on to pattern making and production. To begin, I want to introduce Adam Oraxa, a Geomagic application engineer, as he will demonstrate the first segment of the 3D scan to 2D pattern workflow. Adam, it's all yours.
Thanks, Adam. For the demonstration portion of the webinar, we're going to walk through a scan to pattern workflow using this leather headrest. As you saw in the previous slide, the technology is applicable across a wide spectrum of product types from auto to aero to marine, auto sport, composite products, and more. We're using this model as a quick demonstration, and we can review your specific products and materials during any further inquiries that you guys have in the future. In the demonstration today, we're going to do a typical scan to pattern workflow. First, I'm going to open the 3D scan in DesignX, and then we're going to do any scan cleanup we would need to do. Then we'll push it to create NURBS patches that will create a solid go into ExactFlat for SolidWorks. After that, Mark Jewell will flatten the 3D pieces into the 2D patterns and then add pattern features like seams, notches, and generate production-ready patterns. So let's move on, and I'll hop right into DesignX. So first thing I'm going to do is we have our headrest here, and it is a real automotive headrest. It's it has all its manufacturing seam tolerances. You can see there's some variation side to side and things like that, and we kind of want to make a nice symmetrical, perfect headrest. So what we're going to do is I'm going to just grab a plane here, and I'm going to draw a line in our reference geometry. I'm just going to estimate about where the center of the headrest is and hit OK. And then what I'm going to do is hit mirror. So this is an option we have in DesignX here. I'm going to grab my haphazardly drawn plane here and my mesh, both in the tree. And then the software is actually going to calculate where the exact mirror plane is on that mesh. You can see it shifted a bit from where I just kind of drew it in there. So it gave me a nice exact mirror plane of where the center is. I'm going to turn off plane 1 because that was the one that I drew, and now we have plane 2 here right in the center. And I actually like this right side looking a little bit more here. The seam looks nice and straight and things like that compared to some of the stuff on the left side. So what I'm going to do is then go into Polygons Tools, and I'm going to split this mesh. So I'm going to split it on our plane here, hit next, and we're going to keep this side and not that side. And I'm going to hit OK. So now we chop that other side off. Now I'm going to mirror the side that is left. So I'm just going to come in and pick our mirror position here. So I'm just going to grab that and hit OK. So now we have both of these. The right side is now also the left side, so it looks exactly the same. We have a little bit of an area here where it was mirrored, where the triangles are not necessarily going to line exactly back up for the mesh. So what I'm actually going to do is hit sew, and it's going to stitch them together. Now you'll notice when I highlight over here, there's no real interface of boundaries between the two meshes. Next thing I always do is hit Healing Wizard, and I always do Healing Wizard after I'm done modifying meshes. What that's going to do is just go in and look for any triangles that may be like sticking in or out of the surface, or maybe overlapping each other, stuff like that, and get rid of all that stuff. So we did that. The other thing I always checked is, if the fill holes button here isn't lit, it means we have no holes in the mesh. We have a nice manifold mesh that's watertight. So from here, what I'm going to do is go into our 3D sketch tools. This is sort of a way of doing a manual surface on the part. So I'm going to come into hit 3D mesh sketch here, and I see this is all highlighted up. And what I'm actually going to do is let the software find the contours for me. And I'm just going to bump these values a little bit from what they were, because the mesh just has some texture to it. So we turn the curvature sensitivity down a little bit, and this separator sensitivity is just how wide of an angle there is on the actual part of where it's going to look at the edges and go through and draw contours on. And I'm actually going to come in and redo that because I actually hit check. I wanted to add a couple more in, and the easiest way to do that is just literally to run it again here. So we're just going to hit that, and then I'm going to do that. I'm going to hit the next arrow because I actually want to add this in and split it up a little more. You don't really have patches in your surface that are wrapping around 180 degrees and things like that, like it would be on the top of the headrest here. So what I'm going to do is I'm going to divide this a little bit more. So I'm going to draw a path in here. And this gives me a paintbrush, and I can control the width of the paintbrush and things like that. So now we're going to have a split line there in it, and then I'm going to actually do, one on the back here in the high curvature area. So I'm just going to do something like that. And then I'm going to do another one over here. And I got them pretty close. I'm not going to be too finicky because what I'm going to do is actually mirror one side of the curves to the other side, sort of whichever one I like best. And then we will make sure both sides are exactly the same as far as where the curves are drawn. So we're also going to section it down the center here. So I'm actually going to section it with plane 2 here. That was our mirror plane. And now you'll see we have a section curve down the center. And then I'm going to draw another line top to bottom, just a section. Again, it doesn't really matter the position of it because we're going to, and Mark is going to select patches that are going to follow our seam line, so it'll still be one piece. So we're not actually chopping this up at all. We're just sort of chopping up the surface patches, but we're going to select all the ones that are within the piece that we want here. So we already have all the lines around the seams, so those are going to be our pieces. So now what I'm going to do is not all these lines are drawn together, or there's no intersections between them here. They're just overlapping each other. So I'm actually going to do is split all the lines, and I'm just going to highlight the whole thing, and then it's going to find every intersection that's there. You'll see it's the little red circles here, and then it's going to put a split at each one of those points. And now you'll see we have a nice blue node at each one of those points. What I'm actually going to do is I'm going to come in and grab all these. We have a lot of density on our curves following the surface. I'm actually going to relax that out some. So what I'm going to do is highlight those, and I'm just going to say let's keep the points to like 25 per section and hit OK. Now when I highlight over them, you'll see there's a lot less control nerve. So if you have to adjust and move stuff around, lowering those control points just allows easier adjustment of the curve that's there. And we can sort of poke around at this as much as we want to get stuff smooth if we wanted to. We can do some auto relaxing, stuff like that. But for the sake of the demo, we'll just run through it here. The next thing I'm going to do is I'm just going to get rid of half of this that I don't like. I guess, it doesn't really matter which side essentially. And then I'm going to mirror these curves to the other side. So I'll hit mirror on that. And then I will pick our symmetry plane where we did that split line and hit OK. And I notice some of these curves are blue, and what that means is they are not connected at one end or another. So even though we mirrored them, it's going to drop it on the nearest triangle vertice And that's going to be probably a little bit distance of exactly where the curve is. So I'm just going to highlight all this stuff, and I'm just going to come up the curve ends here and intersections, and put like a value in here. So this is at like 40 thousandths at this point, and I'm just going to hit OK on both of these. And what it's going to do is it's going to recalculate the intersections on the curves and then join them together. So now you can see that they're all this golden yellow color, and that is means that they're all connected together at this point. So once we have that done, we can exit our 3D sketching mode, and I can come into our exact surfacing here, and we're not going to really do any of the auto type stuff. It's great for following a lot of contours and specific curves. You do end up with a bunch more patches, so it would just be more to select when you're in the ExactFlat software, and it just takes some more time. So this is why we're doing it more of a manual method to keep these patches nice and big. So now I'm going to hit Fit Surface Patches, and there's really nothing I have to change in here. I can just let it be an adaptive and leave it go. So now you'll see we have a solid body back here. And if I come in and just turn my mesh off, we have a nice, perfect patch body. So what we're going to do is select out, you can select out really easily what you want to use to fit to your seam patches and seam allowance on the mesh, or on the surface, I should say. And we'll have that get split out and flattened. So Mark will take care of that in a couple minutes. But the next thing I'm going to do is come into our live transfer, and I'm going to send this to SolidWorks, so it's directly imported. What live transfer does is it actually grabs everything from the history tree. So if I actually wanted to use this as a part in SolidWorks, I'd have all these planes in here and my 3D sketches and everything else. And that's for anything you parametrically model in here. It's going to drag the whole history tree over to SolidWorks. So I'm just going to hit go on this, and we're just going to send everything over. Not that we would need anything more than just the solid body. I'm just going to hit OK on that. And if I pop into SolidWorks here, you'll see it's going to come in and draw all of my curves in and make a solid. And then I can come in and hide some of this stuff here if we like, just so we're seeing the solid. And we can hide our planes here just so we have a good look at it. And now we have a nice, perfect solid nurse body in SolidWorks. And again, it's easy to come in and just select the patches of what we want for where we want to put our seams. And then from here, I will throw it to Mark. Thanks for coming out again today, guys, and look forward to hearing from you.
Hello, my name is Mark Jewell. I'm with ExactFlat, and I'm here to show you the rest of the demonstration. As you can see, we are now in SolidWorks, and we have used the laser scanner and DesignX to create a clean 3D model. ExactFlat is used to create 2D flat patterns from 3D models, and we are a certified gold partner of SolidWorks. These are our tools up here in the top left: Create Piece, Convert to ExactFlat, and Refresh Database. The first thing we're going to do is connect to the database. ExactFlat is built on a standard SQL database. The database is where part and design information is stored. Information such as seam allowances, notch types, grain lines, and material properties for flattening, for example. After connecting to the database, information related to our management tools becomes accessible. Because we are working with a headrest in today's example, our database is set up with information related to automotive interiors. Here we have categories for buttons, Velcro, snaps, J-hooks, and other items related to automotive trim. The database also supports hardware types. Hardware types give information such as your pricing breakdown and your vendor list. The Material Manager is where material types and their associated information is stored. This is a particularly useful part of the ExactFlat database. We have general information associated with materials, also information associated with the lay rules for nesting, and physical properties. These physical properties are the mechanical aspects of the material that are used for the flattening process. These properties include the Young's modulus, the Poisson ratio, stress and elongation limits. We can also add, if needed, special properties. The next part of our database is the Export Profile Manager. ExactFlat can export files to any cutter, plotter, or printer. ExactFlat can create custom profiles to make the export process faster and easier. With respect to cutters, All industry-leading cutters, including Gerber, Lectra, and Eastman profiles, are supported. Once the profiles are set up, they can be saved, and the next time you have to export a part for a particular cutter, it's as easy as a click of a button. The ExactFlat database is central to a design philosophy we call integrated additive design. Upstream inputs create downstream outputs, and these are integrated through the ExactFlat database. The benefit to users is no rekeying of data as you move from one aspect of the workflow to another. Also, if you have to make changes, the changes propagate automatically. Let's go ahead and flatten this piece. The first step is to go to the piece creator. To create pieces, we simply select the faces or surface bodies of a particular piece and click Create Piece to join or weld them together. As we create this piece, notice this red arrow. The red arrow indicates the up direction when we're going to lay this fabric on the cutter. Let's finish creating this piece by selecting the other faces and click the Create Piece button. Now we just have the side piece to go, Create Piece, and lastly we'll create pieces, a pattern piece out of the bottom here. And when we're finished, we can see the pieces are locked and transparent. We click the green checkbox and we're finished. The next part of the process is to convert our pieces to ExactFlat parts. When the conversion process is complete, the pattern pieces will automatically be loaded in the Material Manager. Here we simply select the material we want, in this case leather, and click OK. We are now ready to flatten our pieces. To do this, we select the flattener icon. This loads our flattening environment. In the top left, we have a 3D window of our part. In the top right, we have the 2D flat pieces, and in the bottom, we have status indicators. ExactFlat is a two-stage flattener. What we have initially is a projected flat on the right-hand side. Essentially, the pieces have been unsewn and laid flat. The second stage of the flattening process is where we optimize the patterns based on the material properties from the material assignment. Before we optimize the patterns, it will be necessary to create an analysis mesh so that our finite element algorithms can efficiently produce a proper flat pattern. We're going to use the ExactFlat meshing tools to create a better quality mesh for the part in 3D. For this example, we're going to use our uniform remesher. What this is going to do is create a mesh with uniform tessellation throughout the surface. Retesellating the mesh will give a more accurate strain analysis as indicated by the red and yellow highlights on the part. To optimize the patterns, we select our spring icon. This will launch the optimization algorithms which search for strain and sag and try to eliminate both. When complete, we select OK, and ExactFlat will rebuild the pattern geometry with the newly optimized pattern pieces. Once the rebuild process is complete, we can go into our pattern view. And you can see here's our updated geometry. The beauty of working from 3D to 2D is we have automatic pattern associations. We're just going to move these pieces in place. Now, if we did not have pattern associations, it would be very difficult to align these pieces in an orientation which is suitable for doing the pattern design work. And what we'd have to do, and this is common with other programs, is we'd have to select pieces manually, like this, and we'd have to drag them around. Well, let's just get this piece again here. Okay, there we go. We'd have to move them and eyeball them into place. But because we've coming from 3D to 2D, we can use the reference locations from our analysis mesh, which tracks the vertices, and we can place these things with precision. So the first thing we're going to do is we're going to create an offset. The offset is simply just the gap between the pieces. We'll make this 22 millimeters. And now when we have the offset in place, we simply have to click an edge. And then ExactFlat will find the neighboring corresponding piece and put it into place exactly where we've clicked the edge. You can see that there's a little highlight that gets into place. That highlight is indicative of where the pattern piece is going to be placed. Now here we have the patterns laid out in an orientation which is consistent with how they'll be sewn together. We're now going to go into the ExactFlat pattern tools and add pattern features. The first thing we'll do is we'll add seams. To add seams, we simply click an edge, and you can see that the neighboring adjacent corresponding edge is automatically highlighted. You can see the red and the green dots. These indicate the direction of sewing. They will change depending on the type of edge we have. So if we add a further edge here, you can see that the orientation has reversed itself. And if we wanted to reverse them, we can click the reverse direction and simply reverse the direction that we have set for the sewing. Next, we can check the length of the edge. You can see this is 251 millimeters approximately. And we can check also the paired length ratio. In this case, it's 0.99 to 1. 1 to 1 would be a 100% perfect edge, which you typically see in a box. This is almost perfect, 0.99 to 1. This seam edge that we put on is a 6 millimeter join. We can change these things. Here it just changed to a 10 millimeter. And these are drawn from the ExactFlat database. The next thing we can do is add a notch chain. We have a variety of notches. In this particular case, we're going to put a V notch in here. And you can see automatically the notches are added. And we've got a count here specified as 3 notches. If we want to specify spacing, we simply select the spacing button, and then we can set the notches to be whatever distance in between that we desire. If the notch we are looking for is not in the ExactFlat database, it can be added very, very easily. Here we're just changing the number of notches here by changing the spacing. When we're finished, we select the green button for OK, and the seam edges will be a feature now of the patterns. We are now ready to create a marker and compact that marker into a nest. ExactFlat offers 2 types of nesting, manual and automatic. For manual nesting, we simply select the pieces on the marker and move them around. If those pieces get too close to an adjacent piece, they are highlighted in red. We have a collision detection algorithm, which makes it very easy to spot if the pieces become too close in relation to the rules that have been specified. To use the automatic nesting algorithm, we select Nest. This preloads the pieces into our nester preview. When we select Nest again, the compaction algorithms search for the most compact nest available based on the lay rules that have been set. In this case, we have our target yield set to 100, our maximum runtime is 1 minute, and the lay rules come from the ExactFlat database. Lay rules such as rotation constraints, piece gaps, grain lines, and flip constraints are all configurable in the ExactFlat database. When we assign a material type, the lay rules automatically get assigned. For the purposes of this demonstration, we're going to stop the automatic nester here. We're going to click Accept and close down the nesting preview. Here is the marker that will be sent to the cutter. To do this, we click on our Export button, and we have our export profile preloaded from the ExactFlat database. Click Export, and now we're going to create a name for our DXF. Let's just put this on the desktop. Click Save. And there it was successfully saved. Now let's go and open it up and have a look at what the DXF file actually looks like. There it is, auto-generated marker. Click on this, and I think we can view this in our eDrawings viewer. And here is the cut file that will go to the cutter. And as you can see, all the information is in there. We have our grain lines in there. We have our seam edges that we put on there. And this is all in layers, so we could actually turn the layers on or off. There's a cut me layer. There's the grain layer. Let's turn this on and off. The notch layer. Yep, there's the notches coming on and off. And our piece labels as well. And lastly, we put just a few seams on these pieces, so let's go turn those seam layers off as well. And there you have it. This is the actual cut file that we sent to the cutter. Now this is the scan to pattern process, but we're not finished yet. Let's go have a look at some of the other features. Next, we're going to create drawings from these pattern pieces. To do that, we simply select Make Drawing from Part. This will launch the SOLIDWORKS drawing environment. We can create a template or use one of the pre-configured templates. And now we can use the ExactFlat pattern view and create drawings and assembly instructions from the patterns we have generated so far. We can put in things like piece tables. There's a piece table. Piece tables are actually drawn from the ExactFlat database. Material types. Once again, these are drawn from the ExactFlat database as well. SOLIDWORKS has a very powerful drawing engine, and we have just configured that drawing engine to be able to accommodate flat materials that you would use for upholstered parts like car seats, furniture, marine bimini tops, insulation blankets, windmill turbines, fabricated composite materials, a whole host of other things. Here you can see we're putting on material callouts. So if these were different types of materials, say for example if you had a leather on the front of the headrest and a simulated leather on the back to save time and money, you would have different materials being called out here. The goal of the drawings is to be able to quickly and easily create documents for design review or for shop floor assembly instructions. And you can see that we have the exact same pattern layout that we had in our pattern design environment. This again goes back to our design philosophy, which we call integrated additive design, because those design features have been already put in there and they've been associated with the parts in the ExactFlat database. When we create our drawings, we don't have to replicate them. Often people have to create their drawings in a separate program like Adobe Illustrator or something else. That's very common in the pattern development world, but that is not necessary here with ExactFlat. This concludes our overview of ExactFlat, piece creation, 3D to 2D flattening, pattern development, marker making and nesting, and documentation, all part of the scan to pattern process. My name is Mark Jewell. It's been my pleasure to give you this overview, and if you have any questions, we'd be happy to take them.
Thanks to both Mark and Adam for providing those presentations today. Hopefully this presentation has provided you with a good overview of the steps and benefits of the digital scan to patterning process. As you can see, this process provides several key advantages. First, there's the speed of the process. We walked through a typical session in less than a half hour today. Think about how that compares with your current workflow. Second, the solutions are extremely accurate. That should give you the confidence that the 3D scan model matches the physical parts and that the patterns match the model. And lastly, it's a complete solution. You'll have everything you need to prepare and then flatten the 3D scan into 2D production-ready patterns. Now we're going to have Mark from ExactFlat address a couple of the questions that have come in. Please keep in mind that your lines are muted, so if you'd like to submit a question, please use the Q&A button on your screen. And if we don't get to your question, we will certainly follow up with you as soon as we can. Mark, it's all yours.
The first question is, how do you create cut lines or seams on a part? For this, you have a number of options, but the recommended way is to create the seam definitions by drawing lines on your part in the Design X portion of the workflow. They can be done in SOLIDWORKS later on, but it is best to do it earlier in the workflow. The next question is, can you flatten materials other than fabrics? The answer is yes, we can. It doesn't matter if the material in question is a springy, stretchy nylon or a formable sheet metal. ExactFlat can handle all types of materials on any type of geometry. The key to this is the engineering characteristics of the material are stored in the ExactFlat database. These characteristics govern how a material is going to behave under tension and under conditions of sag. The characteristics include things like the Young's modulus and the Poisson ratio, elongation limits, and stress limits. These variables dictate how that material is going to perform when wrapped around your particular surface. So ExactFlat handles any type of material and any type of geometry, and you can flatten things other than fabric, most certainly. We have another question. If I'm working with a material which is not in the ExactFlat database, how do I add it? This is a very good question. So ExactFlat comes pre-populated with some of the most common materials for some of the most common products. But if you're working with a material, for example, a material that you might have engineered or one that just does not happen to be in the ExactFlat database, you can add it very easily. There are two ways to do it. If you know the engineering characteristics of the material in question, that is Young's modulus, Poisson ratio, stress limits, elongation limits, you simply go to the material manager, the ExactFlat material manager, and you enter those variables in the fields that are there. If you don't know those engineering characteristics, we do have a relationship with a number of universities and laboratories that will allow you to test the fabric and get those engineering characteristics for you. It's a simple test. It takes about 15 to 20 minutes to complete the test. And it's about $20, $25, $30 depending on the lab that you go to. And we have companies, certainly when they start using ExactFlat, they will send over all their materials, maybe like 20 or 30 materials, and they'll get them all tested at once. So if the material that you're using is not in the database, you can certainly add it very easily. And if you don't have the engineering characteristics, we have a mechanism through a third party where you can very quickly and efficiently and cost effectively get those characteristics so that you can input them into the material manager.
All right. Well, that's all the time we have for the questions today. Thank you for submitting your questions. And if we didn't get to your question, we will be sure to follow up with you very soon with an answer. So this brings us to the end of our 3D scan to 2D pattern workflow webinar. If you're ready to learn more about how the process will work in your environment, we invite you to reach out to us and set up a one-on-one session. Use the contact information shown here on the screen. Also, as I mentioned earlier, we will be following up with a recording of this webinar, as well as a link to access trial software and a special offer from 3D Systems and ExactFlat. So please be on the lookout for that email. Once again, thank you for joining us and have a good rest of your day.